Hello everyone, my name is Kshitij Goyal and I am a PhD candidate at Carnegie Mellon University's Robotics Institute. Today I'm going to talk about our work on Gaussian mixture models for inference and robot autonomy. The motivation behind this work is towards enabling perception for exploration with heterogeneous robot teams. If we look at an example system from the DARPA Sub-T challenge, we observe a sophisticated strategy that brings together many perceptual capabilities, including local and global inference. They use a LiDAR inertial odometry approach that feeds into an odometry multiplexer. The odometry multiplexer is used as an input to a global localization front end. And after that, a GICP step is run for scan to scan matching. A postgraph optimization is used for localization backend. For local mapping, they use Vox blocks for multiple levels that enables motion planning applications such as positive obstacle detection and negative obstacle detection. And what we see through this work is that the underlying sensor data is used again and again in different representations and separate pipelines. So what we would like to address is this complexity through unifying the perceptual pipelines. So the contribution is that we enable reconstruction, occupancy modeling, registration, and SLAM applications based on a common representation in one open source perception framework that can run on both CPU and GPU. So let's start with how to create such GMMs. We call these self-organizing Gaussian mixture models because in our prior work, we have shown that given an intensity and a depth image, you can estimate the number of components that would best fit that pair of depth and intensity image through a technique called principle of relevant information. Now, a key question is how do we actually take this method and put it in a perception framework on a computer that can run on CPU and GPU. So on the right, we show the same diagram, but in a more computational, highlighting more computational aspects. So point cloud comes in, and first we do PRI on the CPU because it's a sequential algorithm and it runs fast on CPU. Then the number of components M go to K init step, which is the K mean step, which is also very fast on CPU. However, the expensive component is expectation maximization, which we ended up implementing on the GPU. And the final output is the GMM model on the CPU side. The only transfer that happens between the CPU and the GPU is at the beginning when the point cloud is transferred to the GPU. After this step, the point cloud is never used again for downstream application. Everything in the downstream applications leverages the GMM model that is output through this pipeline. And this is also the slowest piece because it is creating the GMM that is used downstream. We note that heterogeneous robot teams contain varying compute platforms. So the benchmarking in terms of compute time that we did it on wide range of uh, desktop GPUs, laptop GPUs, embedded platforms, all the way down to a TX2. We implemented the whole framework, reconstruction, occupancy modeling, registration, and SLAM within a Qualcomm build system. The code base is in C++ and CUDA-C, but we provide Python bindings. We evaluated the timing on both real and synthetic dataset at different image sizes. And the performance measure is the time it takes to fit the SOGMM at different model fidelity levels. First question that we can ask is if we implement naively using scikit-learn, how is the proposed open source framework going to be better? It is about an order of magnitude faster. How much do we gain actually when we use the GPU? Is again an order of magnitude faster. So between a scikit implementation and the GPU optimized implementation, there is two orders of magnitude difference. Uh, how much should we how much do we gain from the GPU on the embedded platforms? The gains actually decrease as we go from Orin to TX2. So the key takeaway here is to offload to the GPU only when CPU resources are in high demand, such as due to VIO, planning, or visualization. As I said, the GMMs are used for downstream applications. For example, let's say you created a GMM of this point cloud. It has been shown in prior work that we can do Monte Carlo ray tracing and figure out occupancy values on the uh, occupied and fill space. This is also bundled into the open source framework. The second thing is registration. Let's say you have two scans, then you created two GMMs. You can do frame to frame registration using closed form gradients and Hessians. This is also in the framework. And lastly, it's loop closure. So as the robot moves over time, it shows up drift and it corrects for that drift using loop closure. This is also included in the framework. Here are some examples of the real-world deployment of the GIRA framework. Here, a robot is going through an industrial tunnel and it is reconstructing the environment using a GMM-based representation shown in the bottom left. And as you can see, it can actually reconstruct to a pretty reasonable degree in real time. And these representations can be actually communicated in real time through these walls up to a base station that's above ground. Um, so as we can see, the robot is traversing and now it's gonna go up the stairs anytime. Yeah, so it goes up the stairs, it goes through a tunnel and everything. So then we actually were wondering how this performs in a multi-robot scenario. So here there are two robots in the same environment and they are going simultaneously. The blue one is the robot on the right, the red one is the robot on the left, and they are doing this shared dense reconstruction of the industrial tunnel. And as you can see, they are uh, about to land now. Yeah, so they reconstructed a small section of this environment. However, you can see the capability of this framework through this example. Thank you.